Okay, it's recording.
Okay. Yeah.
Okay, so I guess I'll start the ones that I solved and then we'll move on. I guess the easiest one I solved was problem H. So this problem is you're given several vases and pedestals, and each pedestal you can either like it has its top has a certain width and its bottom has a certain width. They differ by at most one. And what you have to do is you want to place a vase on a surface that has the exact same width. And for each pedestal, you have to choose whether to put it like right side up or upside down. So you have to figure out like if it's possible, and then if it is, you have to figure out for each vase which pedestal to put it on. So you should be able to do like maximum matching with this, because like for each vase you can determine like for each vase and each pedestal you can determine if like if you can put it on there. But the constraints are kind of high, and like say a pedestal can match with like all vases of like this type, so it matches with a lot of them. You can actually build like a flow graph where it doesn't have like that many, but it turns out like it's just slow. Like it's just extremely tight with the time limit, and there's a simpler solution which we should do instead. So the idea is that the fact that these differ by at most one is actually pretty important. So like let's say I have the sizes on like a number line. So I have like, let's say I have like dots for every vase of a certain size. And let's say I have a pedestal covering like, it either covers one or it covers like two adjacent ones. Maybe it's like this. So what I'm going to do is greedily match these. So like say we want to match we require every vase to be matched. So like let's start with this size. So this vase should be matched with a pedestal, and it's always better to choose a pedestal that cannot be matched with the next size if there is one. Like considering these two pedestals, we can use this one in the future, but we cannot use this one in the future. So it's better to greedily match with it. And then we move on and we match this one with something. And it's better to match them with the ones that cannot be used in the future. And then once we exhaust those, then like if we had another one, then we could use this one. So essentially the solution is to sort of like sort things by their size and then greedily match vases with the pedestals that cannot be used in the future, like for larger sizes. So the complexity will be like, it should actually be O of n because the sizes are small, so you can like do bucket sort. Is that clear?
So the first, I thought you have 3 submissions. So did you try flow first, or any other hidden?
Richard was trying it first, and he was trying to get like a max matching to pass, and it was timing out.
Okay.
But then eventually I just solved it instead.
So I still haven't figured out what so my code failed on one test case. So what I did is I sort the pedestals by, so first I make sure the smaller, so it's a pair and the smaller one is always the first. And then I use a vector of 3, so the third element stores the index. So then I sort them. I assume that will first sort based on the first element, and then sort on the first is the same. They sort based on the second element. Then after I sort them, I sort all the vases, and then for each one, I just pick the smallest one that works. So if it doesn't work, I just keep moving on. So
yeah, I did that too, and it timed out. So I'm not exactly sure what's wrong.
Timed out? So that cannot time out.
Sorry. I mean, sorry, not time out.
Okay.
Wrong answer. My bad. Yeah.
Okay.
Yeah, I ran into the same issue.
I see. So do you see, Raleigh, do you see what's wrong with that greedy logic? So like in this case, the forcing will be yeah, this smallest, this one is. Yeah, it's okay if you don't see it.
So like so basically essentially you sort by like midpoint, like it's equivalent to sorting like by midpoint.
That's correct. Yes, at midpoint. Yes.
Okay.
So first, the sorting of with the vector behavior is that right? I'm not. So it will first use the first element. If I'm sorting a vector of vector in C++, it will. I assume it will first use the first element. When the first element is the same, you will use the second. Is that?
Yeah.
Okay.
That should be. I'm not sure why that's wrong. It seems equivalent.
Yeah. Okay. So I guess yeah, because I look at the test case I failed by submitting to Purdue.caddy, but the output is very different. So I need to write a checker program to figure out what's wrong instead of just comparing the output. That doesn't help. So.
Okay. Well, we can.
Yeah.
Maybe I can think about that later, but I don't see why that should be wrong. Should I move on?
Sure. Yeah.
So next problem is G. So in this problem, there's like a grid of cells, and then every step, like every time step, then every cell that's adjacent to a black one becomes black, and diagonal adjacency also works. So the question is, given like this initial grid, and it can, so the initial grid like is only at most 20 by 20, but when it grows like in the infinite plane, so it can get like very big. And then after like k time steps, you want to know what's the total area of all of the black cells. So essentially, like what if you think about what happens, like you can think about the effect of each black cell independently. Like one black cell in one step, like it becomes a square of like one larger width or two large with two more. So what you can do is to say, like, if this is x, y is the coordinates, then it'll like it will, after k time steps, it will spread to like this line, like x minus k. It will spread to like x plus k plus 1, and then similarly for y. Okay, depending on whether you can, which way you consider up. Okay, so essentially, like for each black cell, we get this, like we get this box. So from all of the cells, we get like a bunch of different squares, and we want to know like what's the area of this union of squares. So normally this would be a very hard problem if there were like a lot of squares, but it would be possible to do in like n log n time if there's n squares. But the constraints are smaller, so we can actually do something a little easier. What you can do is store for each vertical line, we can like make a set of all of these x coordinates that appear, and also make a set of all of the different y coordinates that appear. And that will be like at most a 400 by 400 grid. So each square will occupy some square in here. Let's say it's like this. That will be filled in. Let's see. So like, so to compute the area, if you can find out which in these like compressed 400 by 400 grid, if you can figure out which of those cells are black, like there's a difference in x positions in your set and difference in y positions in your set, and you can multiply them.
Well, why 400 by 400? Why?
So the grid size is,
it's 20 by 20, right? So start with 20 by 20. So why do you want to?
So it's 20 by 20. So that means there's at most 400 black cells initially.
Okay, okay, okay.
And then each one, okay, I should have said, I guess it's actually like 800 because each one creates 2 x coordinates and each one creates 2 y coordinates. So it's 800 by 800.
Okay, that's interesting. Nice.
But essentially, like we compress the coordinates, and we need to compute like for each cell, if it's like in the entire cell between like 2 important coordinates will be all black or all white. So like we just need to compute for each cell whether it's black or white. Let's see, but it's a little bit tricky because like when we fill in a rectangle, we want to make sure we're not like taking 800 by 800 time for each one, because then that might be too expensive. But you can do sort of like what maybe I would call like 2D prefix sums. So like if I wanted to draw a rectangle, I could say +1 at the top left corner. I could say -1 at the top right, like just after the top right corner. And I could say -1 after the bottom left corner and +1 here again. So if you do, so then if for each cell you compute like the sum of the top left of everything like above and left of it, it will be like 1 if it's inside the square and 0 if it's outside. So like if you did prefix sums, then this would end up with 0. This would end up with 0. Wait, yeah, this would end up with 0. This is 1. These are all 0. So if you know how to do like 2D prefix sums, then it just takes the size of the grid and how long it takes to compute it. Does this make sense?
Yeah, yeah. So yeah, but my solution is different. So I didn't code it, but I tell my teammate to code it. So can you go back to the problem description? Yeah. So yeah, my solution is kind of use I guess knowledge from middle school math competition. So the knowledge is once you have fully connected, like the one on the going from the middle to the right, you will be adding one border. And the size of the border will increase by 8 each time, because you are basically going left by 1 and right by 1, and there are 4 sides, so it's going to grow by 8 each time. So basically, what my method is to do the BFS for 20 or 21 steps, so that make sure that the part is fully connected, and then just do the math computation, compute the border size, and then do the sum, do the arithmetic sequence sum.
I see. I bet something like that might be intended because the grid is very small.
Yeah, the grid
so it
is
takes
small.
very little time before it's all
yeah,
connected.
Yeah, but the solution will be more general. The grid doesn't have to be small for that to work.
Yeah.
Well, I guess the number of points. So you need number of the point to be not that big. So that's.
It is also possible to do it pretty fast if the number of points is very large.
Okay.
I've seen that before.
It's
you have to do something like you also need to compress you still need to compress the coordinates, but then you need something like a sweep line too.
I see.
And segment tree or something like that to compute it. It's kind of hard actually. Is that good for G?
Yeah.
Well, let's move on to A. So in problem A, there's like this tournament that takes place in a given tree structure. So the number of leaves is K. So then some competition will happen where there are K players. You need to assign them to leaves, and then and then in each node will be like a match between all of its children, then the strongest player win, or is it the strongest, or is it just one? Let's just say the strongest player wins, because I think it doesn't matter really. So they play, and then the strongest player wins, and then like enters here for the next game, and so like it just happens from bottom up.
Yeah, I guess the tree need to be binary. So because there's a pair each the two team compete, so it's not balanced, but it need to be balanced, binary, I think.
I don't think it has to be binary.
No, but then how do you interpret a node with two children? How do they
they said a node doesn't have exactly one children or exactly one child, but like if there's three people that can play and then the strongest player wins. Like
I think game has to be pairwise. Otherwise I don't right? Yeah.
It says no node contains exactly one child.
Yeah. Anyway, maybe the solution doesn't depend on that, but yeah, let's see.
It doesn't really depend on it. But yeah, that's essentially the process that happens, and then so the question is, based on how the games play out, there's like this happiness score, and that's equal to, like, for each game, I believe it's the sum of the sum of AI? Yeah, the sum of the skills of the players. So like so the sum of the skills of these players is added to like this running score, and then you add it here again, and so on. Okay. So the question is, like, what's the maximum happiness for like out of any way to assign players to the leaves? So what you can do is say, like the way I thought about it is like, for each node, one of its children should be, one of its children will win. So like, let's just say it's like this. It's like each node, except for the leaves, chooses one of its children. We don't know what it is yet, but let's suppose that we did know. Let's suppose that we did know how each node chooses the winner, like which child becomes the winner. Then each leaf has a certain, like, it has like a certain chain until it loses. So like this one, it plays in one game. This one plays in 3. This is 1, and then this one is 1. So, and then if you know how many games they play in, you should obviously assign them greedily. Like, you should make the strongest player have the most games in order to maximize the happiness. You should have like so it's like you should match the best player to the leaf that will end up playing in the most games. Is that clear?
Yeah.
So, and if that's the case, then we should consider, how do we choose which children? Like for this node, will it be better to increase the left child, like the left chain, or the right chain? And the answer is actually, you should increase the longer chain. Like whichever chain is already the longest, you should increase it more.
I see. So essentially, so by traversal tree, you decide each game which child wins.
Yeah.
And then with that information, you can calculate the chain for each leaf node, and then you can assign.
Like, it's best for the strongest player to play in the most games. So
right, yeah. I think that part is that part is intuitive. So what I got stuck was I sort of need to think this dynamically. So then like I think if I find the longest chain and assign the strongest player is, and then I need to figure out what's the second longest after that. So I guess I didn't see this kind of deciding for each node which side win, and that information you can in linear time compute the chain for all the leaves. So that's the one that I didn't see.
So there are some like there are some similarities to like other algorithms, like and things like heavy light decomposition, like you decompose a tree into paths by like choosing the best child for something. So so it's not uncommon to think about a tree as like a bunch of disjoint paths connected together.
Right. Yeah. I guess so. Heavy light decomposition is something I know the name. I don't quite know. So I guess there's central decomposition would be different. I guess it's also decompose the tree, but it will be. I think the idea is different from the inside here.
Yeah. Cool. So that's A, and then I think I is fun. So so like in a graph, an independent set would be a set of nodes, that where no two of the nodes in the set are connected by an edge. So for example, this would be an independent set because like any edge, like there's no edge that connects two nodes in our set. So we say that that's an independent set. And the problem is you're given a graph and you have to find the maximum size of an independent set. So this is actually like a well-known NP complete problem, but what makes it different is that the number of edges is at most number of vertices plus 15, and we know that it's connected. So like in general, if there were a lot more edges, then it would just be like you would need some kind of exponential solution. Oh yeah, so it's also worth noting that n is not that big either. It's at most 100. So the way I thought about this was like, since there's very few like extra edges that are necessary to keep it connected, we can kind of think that we have like a tree. Like we have some spanning tree of the graph, and then there's just like some extra edges that like make the constraint harder.
Is this directed or undirected?
It's an undirected graph.
Undirected, I guess if it's a DFS tree, then there shouldn't be cross edge, it's only in back edge. So I don't know, is it or arbitrary tree or do you actually do it in a DFS tree?
It doesn't actually matter whether the extra edges are back edges or cross edges for my solution. Okay, so we have like a tree, and then we have some extra edges on the tree. So it's also worth having in mind that if you just have a tree and there's no extra edges, maximum independent set can be done with like a tree DP. So the way you can do that is to say like for each node, you have like two DP states. So you can say like DP0 is for that subtree, what's the maximum independent set where the root node of the subtree is not in the independent set, and then DP1 would be the same, but the root node is allowed to be in the independent set. So the way you can do that, the way you can like compute it recursively is say like, if this node is not in the independent set, then each of its children are allowed to be in the independent set. And then if you choose the root node and you say it is in the independent set, then you have to choose the DP0 states of the children because they're not allowed to be in the independent set. So you just take like, so you take the maximum of those two, and then that would be your DP1, your new DP1 state. So in that way, you can compute in linear time a the maximum independent set of a tree. But here we don't have a tree because there's these extra edges and we should know how to handle them. So let's see. So there's actually at most 16 extra edges because there's n-1 for the tree and then there's 16 extra, at most 16 extra for the input of this problem. So the next thing I realized was that if we have some extra edge, we know that both of these nodes cannot be in the independent set. Let's suppose that we know that this one is not in the independent set. We can try both possibilities and then see what the answer is for each case. So for each edge, there's two choices of, like it could be that neither of them are in the independent set, but that just means that we would catch them in both cases. Like if we exclude this one, or if we exclude this one, it would catch both of those. Or both of those cases would catch that possibility. So we have two choices for each edge of like which one is excluded from our independent set. And that gives 2 to the 16 possibilities. And then for each one, we can actually do like almost the same DP for the spanning tree, but there's just some extra requirements, like certain nodes are not allowed to be in the set. So the complexity is actually like 2 to the 16 times number of nodes.
So for each, so given these extra edges, you consider each subset of these extra edges. And
it's not considering a subset of the edges. It's considering for each edge there's a choice which of these two vertices is excluded.
oh, okay, right. So I see. Each edge. I see.
So like for whatever the maximum independent set is, like there will be an assignment for each edge, like that one of them is excluded. And whatever independent set we find on here will be truly independent because because all of the normal edges work and all of the extra edges we know work. So I thought it was a fun problem.
Yeah, so for a maximum independent set, are there other kind of solvable cases or that? So I just, do you remember any other maximum independent set?
Yes, there's other important cases. One of the cases is bipartite.
Right.
So if you have a bipartite graph, there's something called Koenig's theorem. And it states that the maximum independent set in a bipartite graph is equal to the size of the maximum matching. It might be tempting to think like that the answer is like the maximum of the number on one side and the number on the other side, if it's connected, for example, but that's not true. So this would be a counterexample where like, wait, is this a counterexample? Yes. So these three would be independent, but these four are also independent. Oh wait, maybe, okay, I said it kind of wrong. It's like the number of vertices minus the number in the maximum matching. So here the maximum matching is 1. Or I guess 2 times. Is this right?
Yeah, I guess that makes sense.
No, there should be 2, I think.
Yeah, minus 2 times the maximum matching, right? So that's.
Let's see. Well, it was like vertex cover is min vertex cover is equivalent. I remember min vertex cover is max matching.
Hmm.
Isn't that right?
Yeah, yes, it is.
Yes.
Oh wait, this isn't the maximum matching. That was my mistake. The maximum matching is not that edge. It's like, say, these two edges. So then n minus 2 is 4, and then I found an independent set of size 4. So bipartite is kind of like, it might be the most common case of independent set because you can do this in polynomial time. Otherwise, you can do another common algorithm is, so like brute force would be to check every possible subset and then times like time to check that it's independent. But there's also a meet in the middle algorithm where you do 2 to the n over 2 times n. So what you can do is split the set of nodes into 2 sets. And then for each subset of one of the halves, there's some subset of the other one that's allowed to hold. And you can do like, so then if you compute like the same things on this side, then you should be able to.
Okay.
Yeah, you can compute the maximum independent set of that subset. But yeah, there's a meet in the middle algorithm for maximum independent set, and you usually don't need like anything better.
Okay.
I think there's like the Fibonacci idea too, but yeah. Should we move on to K?
Yeah.
So in problem K, we're given a convex polygon. And we're given some point P that's strictly inside of it. And what we need to compute is we want to write P as a weighted average of the polygon's vertices. So like we should assign weights, say like W1, W2. So that, so it's a weighted average. So like the sum of the weights should be equal to 1. And the goal is that like the average to P. So like sum of the weight times X for each of those vertices should be equal to like the X coordinate of P, and then same for Y. And they guarantee that it's always possible because the it's always possible if it's inside the convex set. So if you have a triangle, this can be the simplest case to think about. Or maybe I should first say you can always reduce it to the case of a triangle. So the way to do that is to, like, say you take your polygon and you can draw all of these edges. So you can take you can connect vertex 1 to all of the other vertices and then decompose it into several triangles. What you can check is which triangle is the point P in, and then solve it for those 3 points. And then that's enough because you can assign the weights of the other vertices to 0. So the whole problem reduces to a triangle as long as you know how to check if a point is inside of a triangle. You can check if a point is inside of a triangle by using like cross products. You can say, like say you direct the edges, maybe I should say counterclockwise. If you direct the edges counterclockwise, then the point should be to the left of each edge. And if it's outside, then it will be to the right of at least one edge. So the cross product, one of the most common applications of a cross product in geometry problems is to check like which side of a line a point is on. So you can use that for checking if a point is inside of a triangle. So we've reduced the problem to a case of a triangle. So we have a triangle and a point is inside the triangle. And then my solution was like this. I'll call these points like A, B, C. So my solution was to draw the line from A to P. Then it will intersect BC somewhere. And then I need to write D as like a weighted average of B and C. And then I can write P as a weighted average of A and D. So then by substituting this for D, then I can compute like the weight of B is, so like the weight of B is W1 times 1 minus W2. And the weight of C is 1 minus W1 times 1 minus W2. So if we have 3 points and we can compute the weighted average like between them, then we can solve this problem. To compute point D, we also need we need intersection of 2 lines, which should be in the template that you use. So the only remaining problem is just you have like 3 points that are in a line, and you want to write C as a weighted average of these 2. The way I did it was I did like C minus A dot B minus A over length of BA squared. So that's how I computed that. That tells you like what fraction this length is of the total length. Are there any questions about K?
No, cool.
Okay, I guess next is problem L. Let's see, maybe I need to find my paperwork again. Okay, so problem L is there are n players and they have K lives and they're playing this coin flipping game. So like in each turn, they all flip their coins together, and then everyone who has tails will lose a life, and everyone who has heads keeps the same number of lives. So the game is played until everyone runs out of lives. And then if more than one person loses their life in the last turn, then the casino wins. And if exactly one person is left, if exactly one person is left, then they win. So the question is, you want to know the probability that the casino wins. So in other words, like what's the probability that when they all run out, that at least 2 of them will run out at the same time. So in the problem, we're given n, we're given k, number of players and number of lives that they all start with. And we're also given the probability that a coin flips heads. So there are some like probability formulas that can help to compute this. So in terms of like number of, like maybe a simpler question you might come across is like, given a biased coin, what's the probability that if you flip it n times, you get k heads, for example? And that would be computed with something like if you flip it, I'll say if you flip it m times, you want to know if it comes up I times heads. Then it's something like m choose I, p to the I, and 1 minus p to the m minus I. So the reason for this is that if like sequences of heads and tails, there's exactly m choose I orders for those heads and tails, and then for a fixed order, each head has a probability of p and each tails has a probability of 1 minus p, and then the total probability will be this formula because p appears, or heads appears I times and tails appears m minus I times. So that's like the background for this problem. Okay, so let's go back to the problem. There are n players. Let's suppose we want to know the probability that player 1 wins. The probability that any player wins would be n times this, because there are n ways of choosing the winner and then saying probability that player in particular wins. And then the probability the casino wins would be 1 minus that. So it's enough to focus on probability that player 1 wins. So that would be, the way we can do this is to say sum from I equals 1 to infinity of probability that player 1 loses, let's say lasts exactly I turns, and probability that every other player lasts strictly less than I turns. So because there's n minus 1 players, I'm going to take this probability to the n minus first, n minus 1. So it's like player 2 lasts less than I turns times probability that player 3 lasts less than I turns. But because there's nothing like distinguishing the players, we can just take the power. So assuming we can compute this infinite sum, then we've really reduced the problem to finding a formula for when a player lasts exactly I turns. And then you can compute less than I turns with like a prefix sum on those values. So what's the probability that someone lasts exactly I turns? There would have to be, like the ith spot has to be a tails, because they must lose their life on the last turn. And then the other I minus 1 turns, there must be k minus 1 tails. And then we can use our formula that we did before of like I minus 1 choose k minus 1, p to the I minus 1, 1 minus p to the k minus I. So we essentially have everything we need to actually solve the problem. So all you have to do is to approximate the answer. Instead of taking the infinite sum, you just take the sum to like 10 to the 4 or something. Because like the tail of the series will be very small, because it's very unlikely that the game will last extremely long, since the bias of the coin is not like too extreme. Are there any questions?
I think, yeah. So I was trying to do it in DP, but then the state, there'll be too many states. And I thought there's some clever tricks to compress the state. Maybe, yeah. So it turns out to be really more math.
Yeah, the number of, I was also thinking of that until I realized it's like 50, and then
yeah,
it's really like 50 to the power of 50, like how many states there are.
Yeah, there are too many states, yeah. I see. Okay.
Yeah, it's essentially just math, but like thinking a little bit cleverly
Right. It's yeah.
instead of all possible states.
Yeah.
Okay, so I think that's it for the problems that I solved.
So yeah, I guess Richard, which problem did you solve? Do you want to talk about him?
J and B, but they're not really worth talking about.
Okay.
B is just like trivial, and then J is just Civ, and then yeah.
Right.
J is also trivial.
Yeah, I think no, actually B. I think it's worthwhile to talk about the B a little bit. I think they're probably different way to solve this. So
Really? I mean, you just check if n-1 is like
okay.
yeah, there's n-1 breaking points, and then each person takes away a breaking point, and then you always end up with a size of 1 after breaking the last one. So
Right. I mean, it's once you came up with it. So okay, so is that to me that took me a little bit to I did some small case, and then figure out the winning losing states. But is it that
really,
obvious that
it's because you can only break n-1 points, and then each player chooses a point. So as long as n-1 is
I see.
odd, then Alice wins.
I see. So that's another way of looking at the problem. Instead of thinking them breaking this into different branches, you really just keep them on a number line and really just choosing point on it. So
Pretty much, yeah.
yeah, okay. So but that's okay. I guess I didn't see that formulation of the problem, because to me this is a two-person game, and I can use a sort of standard technique to analyze it, which also
Yeah, I
work,
see.
but it turns out to be, I guess, in some sense overkill. But yeah, okay. So, but this is yeah, it's not obvious to me. You can view this as just picking point on a number line. Yeah. Okay.
As J, we're talking about
J,
it.
it's really trivial, right? J, okay. J, I guess it's not okay.
I haven't read it, so I don't know.
Yeah, basically you just have like an integer with no squares in it, so like none of its factors have like a power of 2 or above, and then you just have to find another integer such that when multiplied also produces a number with no squares in it. And so you just sieve and then find the first prime number that doesn't like it doesn't divide, and then you just yeah.
Okay.
And you only have to go up to like 100 or so, or even less than that, because it's just yeah.
Okay.
Makes sense. So yeah, the other problems would be D, E, and F, and then I haven't.
Yeah. Trung,
So
you want to
Yeah,
share?
sure.
okay.
Can you see this? Oh, why is that? What?
Nice.
Wait, what? Caddis? Okay. All right, there we go. Cool. Let's talk about F. So you were given like an array of distinct integers, and you want to know if there exists like if there exists a 2, 1, 3 pattern. So what do I mean by that? Wait. So like for this, it means that you want to find 3 positions such that the middle position is the smallest number, the left position is the second smallest number, and the third position is the largest number. So for this array, it is that pattern. For example, this array doesn't have that pattern, this array has that pattern, and so on. So my solution kind of works like this. So if you look at like the 2, 1, 3 pattern, you will see that if you fix the left pattern, if you fix the left position, then really these 2 positions does not have anything to do with each other except that they are in that relative order. Like the smaller one goes first and the larger one goes later. So my solution was to fix a number, and then for that number, fix a position, and then for that position, I have the set of all of the positions that which values is less than the current value that I fixed. And also I have a set of values of smaller values, set of larger values, not values, set of larger positions, smaller positions and large positions. So I fixed the left position. I have a set of smaller positions. I have a set of larger positions. So my solution was to greedily find the middle one by picking the position, the smaller position that is closest to the right of the current position as possible. And then when I have the smaller position, I will find the third position by picking like the closest to the right position to the smaller position in the larger set. So yeah, so that's like my crude solution. To speed this up, you can like sort the values in advance, and then you can maintain the set of the smaller and the larger by just inserting them around. So there's a lot of other ways, but I figured that this is actually the best way, like the best solution to code, because no BIT, no segment tree, just only set. I think that's the easiest code.
Yeah, I get it. Okay, let me first so you process you process this based on their
On
size or based on the left?
I process this based on their values.
Value. Okay, so
yeah, from small to large.
When you have a smallest, then there's nothing that's smaller. So
yes,
larger. Okay, so then I see, because so then you can just put all the elements that are larger. Initially, all the other elements are in the larger ones.
Yes, and then when you pick a position, like a value, you just remove that from the set of larger positions.
Okay. No, so yeah, so my solution actually doesn't use any data. Actually, doesn't use any data structure. Well, it uses a vector. So essentially, so I'm scanning from the left and then maintain information. And in the end, I realized what I need to maintain is if I have things that are keep decreasing, so I need to remember those. Anytime I see a new value that's less than one of those, then that value can create a possible 2-1, right? So
yes.
so I guess, yeah, so if so on this data, I will first have 15, and then 24 is too big, so it doesn't really, so the next one I see is 9. So then because 9 is less than 15, so then 15 become my current choice, and then I remember 9. And so for this example, there's nothing interesting, but let's say next one I have is 14, then I would remember 9 and 14, because it could be possible that in the future I get a 13 and then 15 will become a possibility. Okay. So I basically just remember a strictly increasing things, and then whenever I see a new value, I do binary search, find where it belongs. If it belongs somewhere, then that value may become my new better choice, and I can throw away anything after that.
Okay.
So I'm maintaining a monotonic, I guess it's kind of like monotonic queue or stack, I don't know. Yeah, but it took me a while to figure out the logic, because initially because I started thinking by, if I scan from left to right, what do I need to maintain? And in the end, it boils down to this monotonic queue and then the current answer.
Yeah, I guess monotonic too is also a solution, but I was actually too tired to think about any ON solution.
Require a little bit more thinking to get it right.
Yeah. Okay, so that's cool. That's for F. Okay, so for E, it's actually pretty cool, I guess. You will have coins with denominator of 10 to the k, where k is any integer, any natural integer, non-negative integer. Yeah. So you have coins of denominator 1, 10, 100, 1,000, etc. So you want to create this. You want to create a value without using too many coins, as little coins as possible. So for example, with 83, what you can do is to pay 100 and then the other person can give you back like 17, which actually you can pay 103, I believe, which amounts to 4 coins. That is 100 coin and 3 1 coins. And the other person can pay you back 20, which is 2 10 coins. So in total, the amount of coins in circulation to get this exact number is 6. 1 plus 3 plus 2 is 6. So yeah, you want to create this value using as little coin as possible. So my solution is this is very simple. The first thing that I notice is if like I have a value a which ends with 0, I can essentially remove this 0, and I can find the answer for this value a. The second thing that to notice is that if I have a value a and plus x, where x is not 0, then it is better to either change this value x into a0 or change it into a plus 1 0. That is because if you want to change it into a minus 1 0, you have to pass through a0 anyway. Or vice versa, if you want to change it to a plus 2 0, you have to pass through a plus 1 0 anyway. So yeah, if the current value is ax, then I change it to a0 or a plus 1 0. And I also know like the cost. To change it to a0, I need to decrease x, which means that the cost is x. And if I want to change it to a plus 1 0, then I want to add 10 minus x into it. So yeah, from those two things, you can basically do a Dijkstra from this initial node, and the end node is 0, and yeah, you want to find the shortest path. Yeah, that's it.
Okay, so yeah, I guess.
What if a plus 1 has like a lot of carries or something?
What do you mean like a lot of carry?
Like what if a plus 1 ends, or what if a ends with a bunch of 9s?
So 9s like this, and then 1, then
Yeah.
9. Then I just add normally. Like the number of digits is like 1,000, and I can prove that my solution has 1,000 layers. Each layer has like 2 nodes. A layer means like the number that have the same number of digits. So the way that I prove that the number of digits, like the number of number that were Dijkstra through will be 2 per layer, is because that is basically a divided by 10 to the k, check the floor. And also the other value is ceiling of a divided by 10 to the k. So in total, there's only like 1,000 total strings. Yeah, 2,000 total strings. So I just add normally, just like a normal addition. The time limit is also pretty big. Yeah, time limit is pretty big, so I just add normally. Yeah. Oh yeah, I don't have to. Yeah, this is the adding part.
So I did the DP on this. So essentially, for each postfix, I consider the lower digit. Then I can either go with 1 carry or no carry. So just that 2 state, and then the
Yeah, it's similar to my
yeah.
solution, but what I decided was that I was too lazy to code DP, so I just type out Dijkstra from my muscle memory.
Okay.
Yeah, but essentially that is the same solution.
Yeah.
Okay, so is it fine? Should I move on to E?
Yeah, it's fine.
D, I mean. Yeah, okay. So D is fun, I think. So
I haven't read the D, so maybe you can explain the problem description
sure.
a little bit more
So
detail.
you start with like you have 2 players, Alice and Bob. They are very good at shuffling cards so good that every time they shuffle, the new stack of cards ends up in the exact same order relative to the old stack of card.
Okay.
So yeah, so initially you start with like, okay, so because of that, they give you the permutation of Alice and Bob, basically representing the relative order after it has been swapped by Alice or after it has been swapped by Bob. So initially they give you like what is that called? An identity permutation, 1, 2, 3, 4, 5 up to n. So Alice and Bob takes turn to shuffle this deck of card. First Alice and then Bob, and then Alice and then Bob. And what they want to know is the minimum number of time, the minimum number of swaps to return the card, these stacks of card into the identity permutation again. So in this test case, Alice swap 1 and then Bob swap 1, and then it will return to the identity permutation. So that's why the answer is 2. For this test case, Alice then Bob and then Alice and then Bob and then Alice again, which returns to 5. And for this case, it's 10. I won't bother to explain this. So right off the bat, you can see 2 pretty distinct cases to solve here. The first case is if the answer is even. So that means that Alice and then Bob and then Alice and then Bob and then Alice and then Bob, etc. And the last person to swap is Bob. So that means that you can think of this as like Alice and Bob to the k. So yeah, the other case is when answer is odd. So it's actually Alice is the person who swapped last. So the answer is in the form Alice Bob times to the k and then Alice. Okay, so regardless, I'll talk about the solution. So what I imagine of this permutation is to have 2 layers. The left layer representing like the cards after an even number of swaps, and the right layers representing the cards after an odd number of swaps. So from like Alice permutation, I can construct like where does each of these cards ends up in the in the even layer ends up in the odd layer. It's something kind of like this, I guess. And similarly, with the odds with Bob's permutation, I can represent that as edges going from the odd layer to the even layers. So I won't draw that out. So let's analyze this graph. So the edges going from even to odd represents a bijective function. So that means that each node on the left connects to exactly one node on the right, and each node on the right connects to exactly one node on the is connected by exactly one node from the left. And similarly, the graph from odd to even also represents a bijective function. So so together, these 2 bijective functions, will decompose the graph into cycles. Okay, so from this, the first from this cycle property, the first solution becomes pretty clear. For each node, you would want like the size of the cycle that takes this node right back to this node. Like from the even node, you want the size of the cycle that takes it right back to this. And then we take the size of the cycle for every nodes. So then we can see that the answer is basically just like the least common multiple of all of these cycle size. Very cool. All right, so what about the odd case? So for the odd case, you would want to like transport this even position to this odd position that is direct to it, that is adjacent, no, that is opposite to it. So what I find is that if these two evens and odd are not connected, like they are not in the same cycle, then there may not exist any odd solution. That is because simply we cannot reach the odd position from the even position. However, if it exists, then that means that the even and the odd position must be in the same cycle. So let's say that the size of the cycle is S. And we can also like find the minimum distance from this even to this odd position just by like pre-calculating the cycle. And let's say the minimum distance is D. Then I claim that any answer for the odd position must satisfy that it must be modulo, it must be congruent. Like, okay, it must be congruent to the distance modulo the size. That is because I take like the distance, that amount of distance to reach from even to odd, and then I have to go through the cycle. So that means the mod size here. So I have a bunch of these congruent relationship equation. So I just use Chinese remainder theorem, and the rest is just casework. Not like casework, but to handle like the big cases. They said here that if the number is strictly larger than this, then prints huge. And all of my actually all of my wrong answers were just mishandling of that big case. Yeah.
Cool. Yeah, I guess. Yeah. So after I can. So after you explain problem, I see the first part, the even part, the LCM part. Yeah. So odd part use the Chinese remainder theorem. Yeah. That's cool.
Yep. So that's E.
Okay. So that's it, I guess.
Yeah, that's it. I don't think I have solved C.
Yeah.
Neither did Riley. Yeah. So I think that's it's pretty hard.
Yeah.
We took a pretty long time, but yeah.
It's pretty hard to understand too. I understood the problem, but I can't solve it.
Yeah. Okay. Cool. Yeah. Yes.
Okay.